Hello, it's Keith here, and this is lesson 2 of my ARM assembly programming tutorials. Now, last time we did some very basic commands. This time we're going to look in detail at the various addressing modes that the ARM offers us for working with data. Now, we've seen a couple of simple ones. There's some very simple moving of data into registers, moving between registers, and also moving into memory. And these are all addressing modes, but the ARM really offers some very powerful addressing modes, and some of them are a little bit tricky if you're familiar with other systems, or at least I found them rather tricky. So we're going to go through them with some practical examples and see each one in action, and we'll learn how they work, and hopefully we'll be able to come to understand them. So let's go over to today's source code and we'll see each example, and we'll learn about all of these addressing modes in a practical way. Over we go. Okay, so this is the source code. As always, you can download it from my website and try it out yourself. We're going to be trying them with RISC-OS, but they should also mostly work with the Virtual Boy Advance if you don't have the RISC-OS ROM. Now, the only thing with the Virtual Boy Advance is some of them might be addressing memory directly, local memory, and that might be ROM, so they won't write, but the reading should work fine. All of the addressing modes here work on both systems. So let's make a start. Now, the first is the most basic, which is immediate addressing. And this is where the value is stored directly within the source code itself. You can see with a hash symbol here. And we do have some limits to the size of the data we can load in an immediate, as we discussed last time. And because ARM stores the values and the operations to perform within a 32-bit command, sometimes we can't do everything we want. If we want to load a full 32 bits, we might have to split that into two 16-bit parts and do some kind of additional or an OR value. But as I say, we can, generally speaking, load values into registers directly just with a move command. And if we just enable this one and we fire this example up, let's see that on RISC-OS. And here's RISC-OS. And you can see here we've loaded R0 with the value 1, 2, 3, 4. And you can see that's just been loaded in here. We loaded R1 with a binary value here with 101010. And that has, you can see, turned into AA here, which is the correct conversion. And we've loaded a decimal value 65 in here. And that is 41 just there, and that's the ASCII equivalent A. So you can see here we can load directly a value from this source code into a register as long as the value isn't over 16-bit, or at least half of the register is 0 here, as you can see. So we can do that, and that's just fine. So that's the simplest addressing mode, if you will, just loading in values directly, fixed values. Okay. Now, the next one isn't particularly exciting either. We have already seen it, and this is known as register addressing. Now, if you just ignore this first one here, the other ones are all examples of register addressing, and all it just means is that the parameters are registers. So the destination's a register, the source is a register. That's what it is, really. So you can see here we're moving the value of R2 here into R1, and we can just see this in the example code here. So we've loaded R2 with this hexadecimal 8000 test value here. And you can see that just here. And then we've moved R2 into R1 just here. And you can see that R1 now equals 8000 as well. And here we've added R2 to R1 and stored the result in R0 here. And as I've said before, it's important to bear in mind that R1 is unchanged by this operation. Now you can see that 8000 plus 8000 in hexadecimal equals 10,000. So that operation's occurred correctly, but R1 was unchanged. So we can add two values together and store in a third value in ARM, whereas in other systems it would be just add what value B to value A and store it in value A. That's like 68,000, that would be the way it would work. But we specify 3 all times. Now, if we actually wanted to just add R2 to R1, as we discussed before, we would just specify R1 twice like that, and that would work just fine. So, yep, as I say, in a lot of cases, we can use registers as the parameters for these commands. So there we go. Okay, register indirect addressing is another one that's relatively straightforward, and this is where we actually are using the address held in a register as the source of the value. So we're not loading the value of the register, we're using the register as an address value and loading in from that address or storing to that address. So in the case here, you can see we're loading in R2 with the value some data, and some data is somewhere. Here it is, it's some test data here. Let's just fire this one up and we'll see it running. Okay, so here you can see some test data here. And you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, blah, blah. And you can see that that's that data here. And if we just go back up. So you can see we've loaded the address of some data here into R2 here. And we are just dumping that to the screen with this test function here. These are all little functions that I've written that are included in the sources file just for testing so that we don't need to rely on an emulator monitor. So you can see here we've loaded R2 with the address of some data, and then what we've done here is we've loaded in R0 from the address contained in R2. And if you look at R0 here, you can see here it's 67452301. Now the reason for that is that this is a little endian system, the way this ARM's set up. So 01234567 here has been kind of flipped around in bytes, so you can see that's been loaded in just there. But R0 has been loaded in from the address. Okay. Now you can see here we're just making a change here to R0. We're subtracting 0123, effectively setting the bottom to 0 here. And then what we've done here is we've stored back in the same way indirectly to the address stored in R2, denoted by these square brackets here. And you can see here this 32-bit value here has been changed, and the bottom 2 bytes have now become 0, again in little endian format. And you can see here we can use this indirect addressing to load and save from an address held in a register just fine. It's quite nice. Now this is where things are going to get a little bit more complicated possibly. So let's have a look at this one. Register indirect with offset. Now, just in the same way as before, we can use an address in a register as the source of our data, but sometimes we'll want to be a little bit more tricky than that. We will want to actually have an offset from that starting point. Now, I often use the example here, and this is a real example from my Chibi Akima's game. If you've got a set of data for like a player variable, and your player's got an X and Y position and things, and these are all stored in a bank of data. Now, the X and Y position might be at locations 0 and 1, the sprite might be at positions 2 and 3, and so on and so on. Now, you might have a routine to handle the player, but you might use it to handle 2 or more players. And what you would do is you would send a pointer to the start of the block of data for that player, and then the code would read at the different positions within that block for the different attributes of the player. And that's kind of what we can do with this. So what we're doing here is we're pointing R2 to our data, and then we're saying in this example offset 4 bytes from the start of the address in R2, and we're going to read in that into R0. And as well as using a numerical value, if that's a little inconvenient, which is likely to be, we can actually use a symbol. This is where we give a text label a numeric value. Now, we've used labels before, as in this kind of case, where the assembler works out the address within the bytes of the label and gives that label a numeric value. But symbols are where we give a piece of text of our own definition a numeric value. And so we're saying var2 equals to 8. And so this here, where we're specifying an offset of var2 from register R2 in indirect addressing with offset, we are effectively doing the exact same thing as that there, just putting an 8 in, and it's actually the assembler's converting that for us. But this is much nicer to see, and if we use var2 in hundreds of places in our code, and all of a sudden it's no longer 8 and it needs to be 10 in the future, we just change the original definition and that will work just fine. Now these offsets don't just need to be positive, they can be negative as well. You can see we've got a -4 one just here, so that will work fine as well. Now if we're loading a 32-bit value though, they do need to be a multiple of 4. This is a limitation of the ARM processor, so it's something we do have to do. Anyway, let's have a look at this code and let's see it actually working. Okay, so we're using our sum data test data again, you can see up here. So we have started here with the initial values. These are before we've done any work here. And then we've loaded in R0 from R2, which pointed to the start just here, offset by 4. So we've effectively loaded in this area here, 8, 9, A, B, C, D, E, F here. And you can see here, 8, 9, A, B, C, D, E, F, again, little endian, so it's reversed. So R0 has been loaded in there. Now, var2 we set to 8. And so again, we were offsetting effectively 8 from R2 here, and so that will be reading in from this area here, 1, 2, 3, 4, 5, 6, 7, 8, and again you can see that's been loaded in little endian. Now in this case though, we actually loaded in from R2 offset by -4, so that will actually be reading in from before we defined this area, so the sum area negative, so it will be above what we're showing here, and it will actually probably be loading in part of our code. So we've got a very strange value there, this value here, but as I say, that's correct. It's just we haven't defined any data in that position to see. So you can see there we can use this offset with an indirect address, and that will give us some good ability to read in from a bank of variables. It might also be useful if you're pointing to a sort of set of data. For example, if you've got a bitmap font, 1 bit per pixel, and the font is using 8 bytes and you want to work with all of them without changing the offset, there might be cases that would be preferable to do that. But the main case is going to be when you're receiving a bank of data and specific offsets within that data have specific purposes. Sometimes the OS will return a file pointer that will give you the information of a file, the size and the date and the things like that, and they'll all be at specific offsets from the returned address. So it's very handy, and it's very common that we will use that kind of thing. Now, I should of course point out at this point, all of these examples are duplicated on my website. There is text information on all of them with little pictures and highlighting. So if you're seeing this and you're not quite understanding it, you need a little bit more time to process it, which I totally understand. Have a look at the website and have a look at the documentation on there, which may be a bit clearer for you. And also, of course, download the examples and have a go with them, because that's really the idea of this. The whole idea of my tutorials is you see the video, you see the text, and you try it yourself, but whichever one works best for you. But anyway, let's progress with the next one. Indirect with register offset. Now this is almost the same as what we did last time. Last time we were using a fixed numeric immediate offset from our register and reading in from that address. This time we're using one register and another register, and effectively the two are being added together, and the resulting value is the address we're reading from or writing to. So let's see that in action. So here you can see we're loading R2 with some data again, which is just the start of this value here. And then we're loading R1 with 4 here. We're loading that in. And then we're reading in R0 from R2 plus R1 here. So you can see here R0 has been loaded in from this area here, again little endian, and that's because R0 is here and R1 is 4, so 1, 2, 3, 4. That's why we're reading in from there. Now, next we're adding 4 to R1 and reading in again, loading in R0 from R2 plus R1. And you can see here that we've loaded in from this area here, because of course R1 now equals 8, so there's an offset of 8, effectively this top line here, and that's where we're reading in from. Of course, again, we can do not just addition, we can also do subtraction. So we've subtracted 12, and again we've read in that value from before the R0 range, because the R1 now equals, that's effectively -4 here. That's the hexadecimal representation of -4. So that's why we've read in from that address there. So as I say, we've got this flexibility here, and this is going to be quite a handy one if you've got a system where you're like, maybe you've got R2 pointing to the start of a sprite and you're processing the data in that sprite. You could use R1 as your loop counter and also as your offset for reading in the data from each byte of that sprite, if that was appropriate. So as I say, this is going to be quite handy for you as a way of having a starting point and an offset in the registers and being able to manipulate both within the code, whereas of course these are completely fixed, you can't change them. Very powerful, quite handy. And let's move on to the next one. Okay, so that's how we can read in from different memory addresses. Now, so you've seen how we can load in from the address in a register. Now, in the past, the register has been unchanged by this, and when we've used the offset, again, the register that we're using as the source address hasn't been changed. Now, there's going to be a lot of cases where we're going to actually want to change that address when we do a read or a write, and that's what we're going to look at now. Now, before you saw that if we specified a number within the square brackets, that would be used as an offset from the register. However, what if we actually want to change R1 when we do the read in and make it move along automatically? That would be quite handy if we were reading in data from a sprite consecutively, because we don't want to have an extra command incrementing R1 if that's what we want to do anyway. And so what this is saying here is it's saying load in from the address in R1 plus 4 and then update R1 adding 4. It's called pre-increment. So the address in R1 isn't the address that's loaded in, it's the address R1 plus 4 that's loaded into the register R0 here. Now hopefully that'll be a bit clearer when we actually run it. As I say, I know this is getting a bit tricky, and unfortunately the power of the ARM processor does make things a little bit confusing for us sometimes. Okay, so first we're just doing a regular test. We're loading in from the address in R1 into R0 here, so you can see we've got 1, 2, 3, 4, 5, 6, 7. And you can see that's just this value here. So we're just loading in from this address here. Now, next we're loading in with a pre-increment that's specified by this exclamation mark here, and we're using an increment of 4 here. So what this effectively does is it adds 4 to R1 and then reads in from that address here. And you can see that's happened here, 8, 9, A, B, C, D, E, F. So that is effectively the address that was in R1 plus 4. And once this command is completed, you can see R1 has gone up by 4. And we do the exact same command each time with no changes, but because R1 is increasing by 4 each time, we're reading in consecutive sets of 32 bytes from this test data here, and that's the point. We can use one command and read in automatically changing R1. Now what we would actually want to do is of course have a loop here potentially, rather than having the exact same commands each time. I've just put the exact same commands to make it very clear what's happening, but as I say, this is effectively very powerful for a loop because we're incrementing our address register automatically. And it is important to notice that the only difference in the statement here and the statement here is the exclamation mark at the end. It's telling it to update the register after doing the calculation and then use that resulting calculation as the source address to read in from. So that's what that does. We will see this a lot. Now, obviously this is quite handy for reading in data, but if you're familiar with other assembly languages and CPUs, you'll know there's a command called push and pop. We're going to have a look at them later if you're not familiar with them, so don't worry, but we have push and pop, and these put data onto the stack and take it off. And just like on the 68000, the ARM uses these kind of addressing modes to actually simulate, or not simulate really, to work with stacks. So we'll see that later on, and the ARM actually has some very powerful stack commands that are really quite impressive, really are very, very impressive indeed. So we're going to have a look at those in a later lesson, but as I say, don't be surprised, you'll see this a lot because it's literally the push and pop commands. Okay, so in that case, we were actually adding a value to the register and then using that address resulting from that register addition as the source for the data. But there may be cases where we actually want to use the value in the register as the address first and then add something to it and keep the updated register for the next iteration of our loop or something like that. And we can do that as well. Now, you can see here before we had the number in the square brackets and the exclamation mark at the end. Now we've got the number outside of the brackets, and so you can see here that this is saying add 4 to R1, and then because of these square brackets it's saying use that as the source address, and then the exclamation mark says oh but save it in R1. I guess it's kind of saying that. Whereas this time we're saying use the address in R1 as the source of the value and then add 4 to it. Now there's no exclamation mark because there'd be no benefit to adding 4 if you're not going to update R1. Why would you add 4 to R1 and then do nothing with it? So it's sort of logically clear that there would be an update of R1 in this statement. And this is how we do it. The square brackets here say use the address R1, and the value after the register says add a fixed value to the register we just used, R1. So let's fire this up. Now I should point out in all these cases we're doing all of these commands with just the load statement, but these work with a lot of the commands on the ARM processor. So if you need clarity on which commands work with it, I mean, apart from having a go, please go to my website, download the cheat sheet, and you'll see that a lot of the commands are marked as supporting these kind of shift commands and all of these sort of options, and the vast majority of them will support it, the basic ones at least. And we will see as we go along which kind of commands, there's only some exceptional commands that don't really support this kind of thing. So anyway, so you can see here we've loaded in from the address in R1, which again is pointing to our test data here, and we've loaded in here into R0, and then we've used again loading in from R1 into R0 with a post increment of 4. Now because it's a post increment, the command had the same effect on the first run as this command with no increment. So you can see these two commands had the same effect on R0 because they both loaded in from the same address, but R1 has changed after this command because of that post increment. So it's gone up by 4. So on the next read, it's loading in from a different address here. You can see it's loading in from 8, 9, A, B, C, D, E, F because it's gone up by 4. And each iteration it goes up by 4 and reads in from further parts of this data. And so that's the point. If you need to change R1 before you do the read, you use the pre-increment. If you need to change R1 after the read, you use the post-increment. So it just depends what you're trying to do. Effectively, if you're trying to use a stack, you want a pre-increment, and if you're trying to do a sort of consecutive read where your register was pointing to the start of your data, you're probably going to want a post-increment. So as I say, that's how these all work. Okay, now that's how we can read in from registers, and there will be times though that we actually want to work with the program counter itself. Now the program counter is the current running command, and we might want to read from an address close to the current running command directly, and effectively the assembler can calculate this for us, fortunately. So all we're needing to do here is we're just needing to make sure our code is nearby to the data we want to read in, and we can load in from some data directly here, or we can load in from some data plus an offset, and the assembler is going to work out what the actual address of this is for when the code is running. So although you can see there's no mention of a program counter here, that's what the assembler will be doing. And you can see if we just run this version here, you can see we've loaded in R0 from some data, and you can see here it's just 0, 1, 2, 3, 4, 5, 6, 7 in R0, and we've added 4 here directly, and you can see that's loaded in 8, 9, A, B, C, D, E, F here. And again, we're adding more here, and you can see we've loaded in from this part here plus 8. So again, as I say, it's kind of, you don't need to think of it as being a program counter because the assembler will work it out for you, but you need to understand what's actually going on behind the scenes, so to speak. Okay, this is where things get very serious, and this is where, in my opinion, you really start to see the power of the ARM processor. And I will point out we're only using the ARM2, the very early version here, and this is something that really none of the other comparable processors had at the time, as far as I'm aware. So this is what's known as register shifted, and it's something that's referred to in the hardware, I believe, as the barrel shifter. What this is in most assembly languages we have rotation and shift commands, and these can effectively multiply and halve a value. If you shift all of the bits in a register to the left, you effectively double it. If you shift all the bits to the right, you effectively halve it. And if you don't believe me, just try it out and you will see that's the case. Now, whereas most assembly languages, at least the ones I'm familiar with, will have specific commands for rotation and shifting, the ARM processor actually doesn't. It doesn't have a specific command to rotate a register, but what it does have is the ability for a rotation or a shift to be performed on any of the parameters for the majority of the commands of the ARM processor. So where we've been looking at in the past using R0 as the source value for a register, like register addressing, we can actually perform a shift or rotation on the value in R0, leaving R0 unchanged, and then store the result of that in another register. Now I'm saying R0 just as an example, the register number doesn't matter, but as I say, this is very powerful. Now if you don't know what these shifts, rotations and shifting are, don't worry about it, we're going to go through them, we'll see practical examples of all of them. Again, please have a look at the website, there is more examples on there. We've got a big load of examples here for all of them and a description. So as I say, if the description I give you here, you don't feel it makes it clear enough for you, please take a look there. And again, please try the code out, download it, have a go. But we're going to go through each of them now, and we're going to do a variety of operations, and we'll see some practical examples of what happened. So let's just get our sample over here. Okay, so here's our sample. Let's see if we can just organize things a little bit better here. So we've loaded in a test value 8, a load of zeros, a 1, a couple of zeros and a 2 here, and you can see that value is just in here. Now we're going to perform a series of different commands here, and you'll see that the registers will change accordingly. So what we've done once we've loaded this value in is we have performed what's known as a logical shift left by 8 bits on R0, and we've stored the result in R1. Now that's going to be, the result is now in here. So the source register was here, the source register is unchanged, but the result of the left shift of 8 bits has been stored in R1 here, and you can see that result is here. Now 8 bits is effectively 1 byte, so 2 digits here, and if you look here, you've got 00, 1, 0, 0, 2, 00 here, and that is effectively the bottom 6 digits of this here, because that top byte, 8 bits, has been pushed to the left and has been pushed out of the register. And you can see here on the other side of the register has been put in a pair of zeros, because that's what a logical shift does. It moves everything logically, I mean the way you would expect, shall we say, logically by the number of bits specified, and we specified 8 bits, which is effectively 2 digits according to this. Now when we did a shift to the right and we stored the result in R2 here, you can see the same happened. You can see we've got the same digits, but when we shifted to the right, the same thing happened again. This time we're moving everything to the right and we're losing 2 digits off the right hand side. So now you can see that these digits here are these digits here, and the new 2 digits that have been added are zeros again, because it's just logically shifting everything along. Anything new is going to be a 0. So that's what happens if we shift by 8. Let's just close this example down. Let's just quickly change it to a 4. Now I'm using very simple values here. We can of course shift by other bit amounts, but I'm just using very clear example amounts here that will make it quite visible what's going on. So this time we've shifted by 4 bits, which is what's known as a nibble, and that's effectively 1 digit on these displays. So you can see here that when we shifted 8001002 to the right by 4 bits, we just lost the 2. And when we shifted to the left, we just lost the 8 here. So you can see, as I say, we can change this. And yeah, I'm shifting by 8 because it's clear. We can, of course, just shift by 1 bit if we want. Now, the only thing is that you can see the numbers actually change here. As I said before, if we shift to the right, we're effectively halving our numbers. So 8001002 becomes 400801. That's because this 10 has been halved and has become an 08. And when we shift to the left, it all doubles, but this actually got pushed out. And so that's disappeared, and this 1002 has become 2004 here. So as I say, that's why I didn't use 1 bit, I used 8, because it would be much clearer if you're not familiar with hexadecimal. You know, I'm afraid you have to become a bit more familiar at some point, but as I say, as a beginner, I wanted to give you something that you could see the numbers moving around rather than having to think in bits. So, but as I say, you can do that. Now, those are logical shifts which just move the bits around. There is something else known as an arithmetic shift. You might not be familiar with it, but when it comes to hexadecimal, the negative numbers are actually effectively, if you want to convert a positive number to a negative number, you flip all of the bits in the number and you add 1. And the reason this works is because if you are adding a very, very high number to another number and it causes the register to overflow, go over the limit of its value, which in 32 bits I think is 4 billion or something crazy, but it doesn't matter. If you add a very high number, it actually causes things to wrap around, and so by performing that calculation, you actually wrap around to before what you started at. So if you add -1, and that's like all f's effectively, then you will end up, if you add that value to 3, say, you will end up back at 2 because you will wrap around and end up 1 before where you started. It's a bit tricky, and I've got another tutorial on negative numbers, but the point is the only way the processor knows whether a number's positive or negative is if you tell it. You have to use different commands, you have to treat the numbers differently, and if you did a logical shift on a number, moving it to the right to halve it, you would put a 0 at the top value, and that would turn it from being a negative to a positive number because of the way the mathematics works. So as I say, we need a special command to cope with that, and we have one. It's called arithmetic shift right. It should be called maybe signed shift right or something, but that's not what we call it, because if we're doing unsigned arithmetic, then we would still use the logical one. But as I say, if we're using signed numbers, we need to make sure that top bit doesn't change if the number was negative, and that's what arithmetic shift right does. So when we take this value 8001002, because the top bit is 1, that is effectively a signed negative. If we treat it as a signed number, that's actually a negative number. And so if we shifted that logically to the right, and that top bit became a 0, that would ruin the negative number and it would no longer be valid. So we need to make sure that when we shift to the right, if it's a signed number, any new bits contain the original bit that was the top bit. And you can see that's exactly what's happened here. When we shifted to the right, the R2 has now filled the top byte with FF, which is the top bit. 8 was setting the top bit to 1, and so all of the new byte has been retaining that top bit of 1 here. Now, if we change this value here, we just exit that and we change this to 7 and run again. Now a top nibble of 7, or a top byte of 7, 0 if you prefer, has a top bit of 0, so that's actually a high positive number, not a negative number. And so when we shift that to the right, you can see the newly added bits are 0 again, because the top bit was 0. As I say, if you're not familiar with hexadecimal numbers yet, then 7 is 0 triple 1, whereas 8 is 1 triple 0. So as I say, that top bit is now 0, and that's why the newly filled values are 0 here. If you don't understand it, don't worry too much about it yet. I need to discuss these things when we come into these commands to make it clear what the difference with them is. But as I say, negative numbers you'll probably need at some point. But if you want to use a negative, you can just specify it to the assembler just by specifying it in line. And it only comes later to sort of things like comparison operations, and maybe if you're converting values yourself, the assembler will work it out if it's just an immediate negative, and you maybe don't need to worry about it at this stage. Now, it's important to point out there's no arithmetic shift left. When you're shifting to the left, this problem of the new bits doesn't occur, because shifting to the left is not affecting the top bit. It's not creating new top bits. So if you want to shift a signed value to the left, effectively doubling it, you can just use logical shift left and that will work fine. There is no ASL command. It doesn't exist, but it doesn't need to exist. Okay, so arithmetic shifts and logical shifts will push values out of a register and it will just disappear. But there will be times when we need to move values around in the register, but nothing needs to get lost. For example, we might just want to move the bottom bit of a register to the top and move all the other bits along accordingly. And we have a command called ROR, rotate right, to do this. And we can specify a value. So this time we're going to perform a rotate, and we're going to rotate by 8 bits. That's a byte, of course. And we're going to shift our test value, and we're going to store the result in R2. And we're going to do a rotate right. So let's just see that here. So here's our 8000102 here, and we've effectively shifted this entirely by what's effectively 2 digits here, and we've shifted it to the right by 2, so the 80001 has become here, and the 02 was pushed to the right and then rotated round and ended up on the opposite side all the way up here. So you can see nothing's been lost, but everything has been shifted by the specified number of bits. Now, it's important to notice on the ARM that we actually don't have a rotate left. Most processors would have a rotate left, but the ARM only has a rotate right. But it does have a very powerful rotate right, so we can actually rotate right by 24 here. And if you look here, what we've effectively done is actually rotated things left because we've rotated by almost the entire byte, and almost everything has rotated round. So that's actually the effective equivalent of rotating left by 8. You can see that the 80 has ended up over here, and all the other bits are still preserved. So as I say, even though we don't have a true rotate left, the rotate right is sufficiently powerful that it doesn't really pose any problem. Now, we've looked there at using immediate values for our rotations here, but we actually have the ability to use a register as the value that is going to provide the shift that we want. So instead of specifying an 8 or 4 or whatever, we can actually specify the value in a register. So here we can load R3 with the value 4, and then we can rotate R0 by R3 bits to the right with ROR, or we can arithmetic shift it in the same way. So if we just fire this up, and we can see this example here. So this time we're moving just by a single nibble. So you can see here 8001002 here, and we've shifted 4 bits, 1 digit effectively to the right, and that digit has been pushed over here by this ROR command. And you can see that when we do the ASR, again, that just works in the exact same way, and that has effectively become an F here. So you can see there we can use a register as the specified number of bits rather than a fixed value, and that's going to be quite handy to us. Now if I just put this on top here and we have a look at the final example here, RRX. Now a lot of other systems will have carry bits, and there will be commands to work with those carry bits. The ARM does have a carry bit command. It's RRX, rotate right with extend. This will rotate a register to the right, and it will push just a single bit out. You'll notice there's no specified parameter, and that will get stored into the carry bit of the flags, and then we can use that in another command and rotate that bit into a different register. Now you can see here we're loading R0 with 0 here, and this is just a sort of test to get things started. Now we're using a move command, but we're specifying move S, and this is something we're going to cover later. But when we put S at the end of a command, the command will update the flags because we need the carry flag to update. And so what we're doing is we're rotating R0 to the right by 1 bit. We can only use ROX to rotate by 1 bit, and storing the result in R1. Now actually we don't care about the result in this case. I just wanted to set the carry to 0 as a first test. And then what we're doing here is we're actually loading a new test value in R0, and we're rotating that to the right by 1 bit and storing it in R1. And then we're rotating R0 to 1 bit to the right again and storing it in R2. Now this first command will have pushed a bit 1 out of the register, because you can see here that this bit is on the right hand side. That's going to get pushed out into the carry, and when we do our second command, it's going to get pushed into the value in R2, and that's going to get stored just here. So you can see here this value was rotated to the right, and you can see that this 1 got pushed out. This 2 became a 1 because every time we shift to the right it halves. This 8 became a 4. Now when we did the second rotate, and the carry would have been 1 at this point, the new top bit will be the value in the carry, which is a 1, and so that becomes a C, because if the top 2 bits of a nibble are 1 and the other 2 bits are 0, then the value is C. Whereas if the top bit's 0, the next bit's 1 and the other 2 bits are 0, it will become a 4. So as I say, that's what's happened there. I know this is a little bit tricky, and to be honest, this isn't a command you'll probably need very often, so I don't think you probably need to worry about it if you don't understand this command, but I just needed to go through all of them in some form to do a complete example on all of these options. So that's how those commands all work. Now in those examples we've just been using them for immediate values. As I've said, you can use these commands on a large number of ARM commands, and while you will need them to just alter values for your own use, maybe if you're changing colors with bitmap fonts and things, you might need them, but also, as I say, you can use them on any of the parameters for the majority of the commands of the ARM, so, and without changing the underlying registers as well, which is quite handy. Now, as well as being able to use these on values, we can actually use them on addresses, and this is quite handy indeed, because there will be times where maybe you need to read in, maybe you've got some 32-bit values in a table, and you want to read the first 32-bit value, and then the second 32-bit value, and then the third 32-bit value. Well, you can have R1, or any other register of course, pointing to the number of the value, and then you can do a shift left by 2 bits, and that will effectively multiply the register by 4, and that will allow you to use the register as an offset, and it'd be very straightforward. And that's actually what we're doing just here. So what we're doing here is we're saying use the address in R2 plus the address in R1 multiplied by 4. And that's because we're doing effectively 2-bit shifts to the left. 1-bit shift to the left will multiply by 2. 2-bit to the left will multiply by 4. So we're saying multiply R1 by 4 here and add it to R2 and use that address as the source of this command. Now, it's important to understand R1 isn't changed by this. Of course, R0 is, but R2 and R1 are unchanged. So this is being done on the fly, as it were. So let's fire this up and let's actually see this in action then. Okay, so you can see here that what we've done here is we've actually got R2 pointing to the start of this bank here, and R2 never changes. And then we've got R1 containing a variety of values here. First it contained 1, shifted left to twice, which is effectively multiplying it by 4. So we are now here, we're loading in this value here, because R1 times 4 equals 4, of course. So there's a 4 offset from the R2 value, which would be pointing to here. And so we've loaded in 8, 9, A, B, C, D, E, F in little endian, this value here. We then added 1. So that the next time we read in, we were effectively adding 8, because we're shifting the value that's now 2 in left by 2 bits, which is effectively multiplying by 4. So 2 times 4 equals 8. And so we're loading in 1, 2, 3, 4, 5, 6, 7, 8, and you can see that just here. Then we're subtracting 2 from R1. This is now effectively setting R1 to 0. And we're reading in again, And of course, because R1 is now 0, we're effectively loading from here, 0, 1, 2, 3, 4, 5, 6, 7, and that's the value just here. And you can see there that we've been able to load in just using a simple value from 0, 1, 2, 3 and do the multiplication to calculate the position of the 32-bit values that we want to read in via this logical shift left here. And it's not just logical shift left, we can do it really any of the commands here, and you can see if we just run this again, and the effect is really the same, but you can see here that we can use an arithmetic shift left and we can use the rotate commands as well, provided we've got the right values to use those. These commands will all work in this way, and as I said before, this is really the power of the ARM processor in my mind, is that we can use any of these shifting commands on the parameters without changing the registers and use that as a source address or as a source value for the other mathematical commands that the ARM provides. And I know I personally find it very confusing, and I still kind of do a little bit, but as I say, it's very powerful for getting a lot of work done in a very few commands. So that's really the power of this processor, if you ask me. We've really covered a lot there. I apologize that I know that was rather fast. I try and get through these as quickly as I can to get everything in one lesson. Unfortunately, the ARM is so much more complex when it comes to its powerful addressing modes than the others. This has possibly been a bit daunting, but I felt it was best to get it all out of the way. Now, we've looked at all these addressing modes. If you're writing your own code, you're possibly not going to need them all, so don't be scared off if you don't understand them all, if you can't even remember them all. Just put them on the back burner for now. Just remember them for the future. Maybe come back to this video if you need more help. If you want to play around, of course, go to the website, have a look at the examples there, get the source code, try it out for yourself. But if you're a bit daunted, don't worry too much and just come back next time, because we'll probably be looking at some stuff that's actually simpler, ironically. But we can't discuss the stack without looking at the addressing modes, because the addressing modes are used by the stack commands. So as I say, it all kind of comes in together. So I thought it was best to just get it all out the way at this point, and then we can move on to other things later on, and not have this kind of content split up into different places, because I thought it was best to look at all of the addressing modes in one go, get it all out the way, and have one common point that you could come back to check it all out again. Anyway, I hope you found this interesting. If you have, please like and subscribe. If this was a bit daunting for you, and you want to try a different processor, check out the Z80 or the 68000. The ARM with these addressing modes is very tough, but hopefully you'll come back and check out next time, because we'll be looking at the ARM again. We'll be doing something probably a little bit simpler, ironically. But anyway, I hope you've enjoyed it. I hope you'll have a go, and I hope you enjoy programming the ARM. Anyway, thanks for watching today, and goodbye.